billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Definition. Dear student, first of all we have definition equivalent set. Let we are given two sets A and B. These elements are said to be equivalent if there exists a function f such that from A to B that it is 1 to 1 and on to. We then symbolically write A is equivalent to B or A is equivalent to B. Now we have a theorem. The set equivalence relation defines an equivalence relation. Proof. We have to prove that the equivalence or the similarity of the two set is an equivalence relation. So the similarity of the set is denoted by putting the relation this between the two sets. We remember that a relation is called an equivalence relation if it is reflexive, symmetric and transitive. At the same time, thus to complete the proof, we will prove the following. Reflexive property, that is A equivalent to A. So symmetric property, A is equivalent to B and B is equivalent to A. Transitive property, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. First number, reflexive property. Let A be an non-empty set and let A to A be an identity function, that is IA is equal to A for all the A belong to A, and we know that the identity function is always bijective, so A is equivalent to A. Number 2, symmetric. If A and B are two non-empty sets such that A is equivalent to B, then we are to prove that B is equivalent to A. Since A is equivalent to B, so by definition there exists a function f such that A to B such that f is a bijective. Since the inverse of a bijective function again turns to be a bijective function if inverse B to A is bijective, and thus B is equivalent to A. Transitive property. Let A, B and C are the three non-empty sets such that A is equivalent to B and B is equivalent to C. Then according to the definition of the equivalent sets, we will have two functions f from A to B and g from B to B, C such that both are bijective. Since we know that the composition of the two bijective function is again be a bijective function, so G composition f A to C is bijective, A is equivalent to C. All the above example properties prove that the symmetric of the two set is an equivalence relation. Next we have example. We have two set equivalent and non-equivalent set. A is equal to A, B, C, D, E and B is equal to alpha, beta, gamma, del and phi. Then A and B are equivalent set, that is A is equivalent to B because both contain the same number of elements, that is both have the same cardinality. As far there exists a bijective concerned, we can find a function f such that from A to B defined by f of A is equal to alpha, f of B is equal to beta, f of C is equal to gamma, f of C is equal to del and f of C is equal to phi. So we can find many other bijective functions on the set A and B, making them equivalent. For example, G such that A to B defined by G of A is equal to phi, G of B is equal to phi, G of C is equal to alpha, G of D is equal to gamma and G of E is equal to beta. Note that both these functions cannot be defined by a single formula due to the structure of the set. We have next example, that is prove that n is equivalent to 2n, where n is a set of natural number and 2n is a set of the even natural numbers. So given that n is equal to 1, 2, 3, 4 dash dash and so on, and 2 is equal to 2, 4, 6, 8 dash dash and so on, and let f from n to 2n defined by f of n is equal to 2 pi, then obviously f is 1 1 because f of n1 is equal to f of n2, 2n1 is equal to 2n2, this implies that n1 is equal to n2. It also onto because every element in 2n is the image of some element in n. This is also seen from the diagram n is equivalent to 2n. Now we show that n is equivalent to z. So we have n is equal to 1 2 3 4 5 6 7 dash 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 and so on, and z is a set of integer. So we define a function n to z defined by f of n is equal to n by 2 if n is even, and is equal to minus n minus 1 divided by 2 if n is odd function. F of 1 is equal to minus 1 minus 1 by 2 which is equal to 0 as 1 is odd. F of t is equal to 2 by 2 which is equal to 1. So from this relation we proved that this is a bijective function and n is equivalent to z, which is our requirement.